Hi, everyone. I hope you can hear me, and let's get started. Okay. So let's start by recalling where we were last time, and then we will pick it up from there. So last time we ended up with some bad news. Last class, we saw the Shannon's theorem, right? And basically, Shannon's theorem told us that as long as we are considering perfect security, any encryption scheme whose key size is less than the message size, or any encryption scheme in which you reuse the key time and again, that can be broken in some sense, right? And the idea here was try all possible keys. And now the good news is that if we restrict our attention to adversaries who don't have all the computing power in the world, or who don't have all the time in the world, maybe this attack is not practical for them, right? So this is just an idea to move forward, and let's call it a great idea. The idea would be to consider only computationally bounded adversaries. So these adversaries cannot try every possible key. If the number of keys is like, let's say, 2 to the power 100, they are not capable of going through all the keys. And hence, we can still hope to get security against these kind of adversaries, right? So if we are to rely on the adversary being computationally bounded, what do we need? We need some task which is hard for these kind of computationally bounded adversaries, but might be easy for unbounded ones. Right? Because Shannon's theorem tells us that for unbounded adversaries, we cannot hope to get anything close to perfect security. And Shannon's theorem, in fact, also gives us an explicit attack in some sense. So now our hope is to look for hard problems, which computationally unbounded adversaries cannot solve, right? And we might already have some candidates in mind. So as an example, if P is not equal to NP, I'm sure all of us have already seen things like NP complete problems, or even other problems like factoring. So this is what we will try to rely on. Okay, so to be able to argue about these kind of problems and constructions based on these problems, let me introduce some notation, some basics like what is polynomial time and so on. So some notions, some very basic notions, and we will make use of these throughout the class. Let me use a different marker. So the first notion is that of polynomial time. And let's also denote it by just PT. So we say that an algorithm A is polynomial time if and only if there exists some polynomial P, and I hope we all know what a polynomial is. A polynomial has the following form: P of x equals x to the power n plus, A of x to the power n plus B of x to the power n minus 1, and so on. Such that for all large enough inputs, for all large enough x, comma, running time of A of x is bounded by P of x, rather P of length of x. So typically we will denote the length of x as n, and we also call n to be the input size, right? So essentially what this is saying is that you look at any algorithm A, its running time might depend on some specific input, but we need that for every input, this algorithm A halts in polynomial time. And we will also refer to this, this algorithm as an efficient algorithm. Then there's also the notion of probabilistic polynomial time. Probabilistic PT, or let's call it PPT. And we will, so this is essentially the same as PT, except that now we are talking about the expected running time of the algorithm. The algorithm might be randomized, and the running time of the algorithm might depend on the random coins which it produces in any given run. And we need the running time to be polynomial time. So again, an algorithm A is said to be probabilistic polynomial time. Again, if and only if there exists some polynomial P of x such that for all large enough x, now expected running time of A of x is bounded by P of size of x. Okay, as an example, we can take coin flipping. So let's consider the following experiment. I keep flipping a coin until I get a heads, right? So in that case, we cannot bound the running time of this algorithm. For all we know, I might just keep flipping a coin and I might never get a head, right? On the other hand, the expected running time of this algorithm is probabilistic polynomial time. It's PPT. So I flip a coin until I get heads. So this is PPT, but not PT. Okay. So in cryptography, generally we will consider algorithms or adversaries whose running time is probabilistic polynomial time. So any questions so far? Yes, good question. Yeah. Every polynomial time algorithm is also probabilistic polynomial time. If the overall running time is bounded by some polynomial, then expected running time is also bounded by the same polynomial. Now we will talk about what is known as negligible functions and noticeable functions. So these notions, polynomial time and probabilistic polynomial time, they will generally be used to talk about the running time of algorithms. Negligible and noticeable functions, we will typically use them to talk about probabilities, probability of success and so on. So what is a negligible function? Intuitively, this is a function which is like very small, almost exponentially small. So a function, let's call it nu of n, is called a negligible function. Negligible. If for every polynomial p of n for all large enough n, comma, nu of n is actually less than 1 by p of n. Okay, and we denote these by negl of n. Okay, and as an example, so what is an example of a negligible function? A very simple example is 1 by 2 to the power n. Right? Because you can pick any polynomial. For large enough n, 1 by 2 to the power n will be smaller than 1 by poly. And typically, we would like the success probability of the adversary to be negligible. And then finally, let me introduce noticeable functions. So these are functions which may be small, but not necessarily like exponentially small. So a function fn is noticeable if and only if there exists a polynomial. Let's call this polynomial p of n such that for all large enough n, actually there exist polynomials p of n and q of n. Such that for all large enough n, this function f of n is less than or equal to q of n, but greater than or equal to 1 by p of n. And then we will denote these by notice n. Okay, so they might be as large as a polynomial, and they might be as small as 1 by polynomial. And of course, if we are talking about probabilities here, then f of n cannot be greater than 1, and it can be as small as some 1 by p of n.
But if we're talking about probabilities, then making a upper bound like q of n necessarily encompasses 1. And so is it worth like having a q of n? Because we could just say it's less than or equal to 1.
Yeah, if you're only talking about probabilities, then probably q of n can be dropped. But we are just trying to keep the definition general.
Okay.
And some simple facts to keep in mind. So the first one is, suppose I have two negligible functions, negligible n times negligible to n. What is that equal to? That's also negligible. Now, what if I multiply a negligible function and a noticeable function? Do I get negligible or do I get noticeable? So this is, let's call it negligible 1. Okay. And then similarly, if I add, let's say negligible plus noticeable, I get some noticeable function. And then if I add negligible and negligible, I will continue to get negligible, and so on. Okay, any questions? So now let's move on to something which is the focus of this class, which is one-way functions.
Wait, why is the second fact true?
Negligible times noticeable. Yeah, so if some quantity is noticeable, then that quantity is at most equal to some q of n, right? On the other hand, negligible is even smaller than any 1 by poly. In particular, negligible is even smaller than 1 by q of n. So this times this will be smaller than any 1 by poly of n. Is it clear, or should we do it in more detail?
Oh, no, that's fine. Thank you.
All right, so what are one-way functions and why do we study these objects? So in some sense, one-way functions are sort of the easiest cryptographic primitive to design, or easiest cryptographic primitive which you can think about. So in encryption schemes, in some sense, the ciphertext must hide the full message, right? And you can define encryption in different ways, but any good encryption scheme, even if it leaks like, let's say, half of the message, or even if it leaks like 1 bit of the message, we will never call it a good encryption scheme. On the other hand, in one-way functions, output must hide at least something about the input. In other words, the output or the ciphertext, you can call it whatever you want. The only thing which we want is that it should not leak the entire input or the entire message. If it leaks like half of it, that's fine. So in some sense, one-way functions, they ask for a much weaker requirement compared to encryption schemes, and that is why we will start with one-way functions. Okay, and very roughly, what are one-way functions? This is just the intuition. We will have a formal definition. So in one-way functions, there are no keys. There's no decryption process. In fact, when we talk about one-way functions, it may not be immediately obvious why one-way functions have any use whatsoever. But we will see that once we have one-way functions, you can actually design encryption schemes and you can do a lot more. So a one-way function takes an input from some domain and gives an output in the range, and it should have two properties. So number one is f of x is polynomial time, or let me just say f is polynomial time, which means that for any input x, let's say, f of x is easy to compute, can be computed in polynomial time. Okay. Another property is given, let's say you're given some y, which is f of x. Given y, inverting y is hard. One way of thinking about it is if y equals f of x, x is called a pre-image of y. And what we are saying here is that given y, finding any pre-image of y is hard. And we'll be formal in a moment. What does it mean inverting y is hard? So now let's take the formal definition of one-way functions. So a one-way function might take some n-bit input and might give you an m-bit output. So this function is called a one-way function if it satisfies the following two conditions. Condition one, as I talked about, is that f must be polynomial time. Note that not probabilistic polynomial time, just polynomial time. The second condition is as follows. So it's represented by probability for every PPT algorithm A. You can also think of this algorithm as an adversary. Probability that f of x equals f of x prime such that x is chosen uniformly from 0, 1 to the power n, which is the input domain. X prime is the output of the algorithm on f of x. So this probability is some negligible function in n. So let's try to understand what this equation means. So this equation is saying that first you sample a random string, which is of length n. Then you compute f of x on this random string. Then you give the output to the adversary A. And now this adversary A tries to guess what x is, x prime. So let's say x prime is the guess of this adversary. And now we are looking at the probability that x prime is a valid pre-image of f of x. So we are looking at the probability that f of x equals f of x prime. Okay. So maybe to understand it better, let's consider the following question. So what if we only required the following: probability of x equals x prime, and the rest remains the same, and we ask this probability to be negligible. Okay. So essentially, we give adversary f of x, and adversary has to give us x exactly. X prime must be equal to x. So that's one way we could have defined one-way functions. Now the question is this a good definition? So any thoughts? Is this a good definition, bad? And if bad, why is it bad? So essentially, is it meaningful for us to ask the adversary to give us the exact input which we started with? Yeah, it's a stricter restriction, that is true.
It could be that there are like two inputs that map to the same thing. And so in that case, an adversary couldn't meaningfully distinguish.
Okay, maybe I'll give you a hint. What if f of x equals 0 always?
Yeah.
Right? So in that case, just this trivial function actually satisfies this condition, right? Because the output just has no information about the input. So how is the adversary going to guess what the input was, right? Adversary will not be able to do that. So unfortunately, obviously, this function is completely meaningless. We cannot hope to use this function to do really anything interesting in cryptography, right? On the other hand, if we look at this notion and we look at this function, then clearly this function doesn't satisfy this probability equation, because any adversary can just output any x, right? And every x is a valid preimage because every x gives you the same output. So that's why we will get rid of this and we will just make a note that it is not maybe F might have a lot of collisions. What is a collision? Collisions is a collision happens when two different inputs are mapped to the same output.
So I have a small question.
Yeah.
So when we are calculating this probability, so the adversary knows the function f, right?
Adversary knows the function. That's correct.
Yeah, like he can design his algorithm knowing the function f, right?
Exactly.
Cool, thanks.
Yeah. And yeah, this is a general comment in cryptography. Later on, we will discuss encryption and we will discuss various kind of algorithms. Algorithm is always known to the adversary. It's only the random input or the random key which you sample, which may not be known to the adversary, right? And by the way, what is this probability taken over? This probability is taken over the choice of x. Because really in this whole experiment, the only random thing which I am sampling is x. Okay, yeah. So coming back to the note, F might have a lot of collisions. It's not meaningful to ask A to return the exact input we started with. And by the way, this definition, as I said, as I explained, this is also called strong one-way function. And we can also define something which is known as weak one-way function. So strong one-way function says that the probability that the adversary can guess the output is really small, it's negligible. Weak one-way function requires that this probability is not 1. So at least some noticeable fraction of the time adversary fails, maybe not all the time. Okay, so probability, again the same thing, is less than or equal to 1 minus noticeable. So what we are saying essentially is that A fails with noticeable probability. Here we were asking A to fail with probability very close to 1. And as you can imagine, weak one-way functions are in some sense much easier to design compared to strong one-way functions. And another thing to note here is that one-way functions can also be defined for a special domain. So your one-way function will go from an input from this domain D to some range R. And here we were assuming that our domain was uniform inputs, but the inputs might be coming from some other distribution or some other domain. And in that case, we require the security of one-way functions to only hold if the input was sampled from this domain. So to write it in a more general way, now X is sampled at uniform from D, and everything else remains the same. And this must be at most negligible. We can also define stronger notions of one-way functions. Injective or one-to-one one-way functions. So essentially, here we require the function to have no collisions, which means that in an injective one-way function, if x is not equal to x prime, then f of x must also not be equal to f of x prime. And for injective one-way function, in fact, this definition, this probability is actually equal to asking x and x prime to be the same. We can also define a one-way permutation. In one-way permutation, we require it to be a one-to-one one-way function with domain and range being the same.
Professor, can you move the camera down just a little bit?
I'm done. So are you able to see the last line?
It's cut off like halfway.
Oh, really? Okay.
Thank you.
So we will try to design one-way functions, weak one-way functions, injective, and so on. They have different applications, as we will see later on. But let's first try to understand what one-way functions are, right? What do they hide and what they don't hide? So first of all, because there's no key, there's no decryption process as such. Given f of x, there's no way to recover any preimage. There's no way to recover x or x prime. So first, a major limitation of one-way function, which we all should keep in mind, and sometimes all of us forget that. The limitation here is that f of x might leak most of x. Okay, the definition only requires that probability it leaks all of x or all of x prime. It leaks any preimage in full. This probability is negligible. But for example, a one-way function f might leak half of the input almost all the time. And in fact, given a one-way function f, I will design another one-way function f prime, which always leaks half of its input. And let me be clear about the input domain. So f acts on n-bit inputs. And I will design f prime, which actually acts on 2 n-bit inputs and will give you an output which is n plus m bits. So now consider the following f prime. F prime takes x concatenation x prime as input. Both of these strings are n bits each, both of them are random. And it acts as follows. It gives you f of x and it gives you x prime in plane. Right? So this one-way function clearly leaks the second half of its input. Or I should say this function leaks the second half of its input. And now my claim is that f prime is a one-way function if f is. And yet f prime leaks half of its input. So why is this claim true? Well, if f is a one-way function, then given f of x, you cannot compute x. Okay? So now given this full output, you are not able to compute x, but to invert f prime, you have to compute both x and x prime. So this claim seems to be true. Any questions? So this is a major limitation which we should all keep in mind. Another fact to keep in mind is that if p was equal to np, one-way functions cannot exist. And here, let me just talk about the proof idea. It's very simple. So if p equals np, this means that if I can verify a solution, I can also come up with a solution, right? So the first observation is that finding the preimage of a one-way function is in NP. Okay, this is because given a preimage, it's easy to verify. If somebody gives me a preimage, let's say x prime, I can just apply f to it, and then I can verify that f of x prime is indeed equal to y. If and hence, if p equals np, you can also compute some preimage in polynomial time, right? And hence, this probability here, it will just be 1. Because there exists not even a PPT, but there exists just a polynomial time algorithm, which can find a preimage always. So now the next question is, it's a major open problem. Let's say we assume that P is not equal to NP. Do one-way functions exist based solely on this assumption? So if P is not equal to NP, that means that there are NP-complete problems which cannot be solved in polynomial time. Can you take one of these NP-complete problems and build one-way functions from that? So this problem has been open for like 40 years. So we unfortunately cannot solve this open problem. At least we don't know how to do it. But we will make a slightly stronger assumption. We will instead use something like factoring, right? And by the way, factoring, it's a strong assumption. It's an assumption which is stronger than just assuming P is not equal to NP, because we don't know if factoring is NP complete or not. It may very well be the case that P is not equal to NP and yet factoring is easy. But we will just assume factoring is hard and we will try to design a one-way function based on that. Okay. So let me now define the factoring assumption, and that should give us some kind of one-way function. So factoring assumption at a very high level, it says the following: you pick two large primes, you multiply them, and let's call this some number capital N, right? Given capital M, it's actually very hard to recover these two large primes. So define P sub N to be the set of all n-bit prime numbers. It's a number P such that P is less than 2 to the power n and P is a prime. Okay. Now the factoring assumption says the following: for every PPT adversary A, the following holds. The probability that this adversary, we give this adversary some number capital N, and this adversary gives us P comma Q, assuming that P comma Q are sampled at random from the set of all n-bit primes, and N is set to be P times Q. So this probability is less than or equal to negligible. Okay, so you start by sampling two primes, you multiply them, you give the multiplication as input to the adversary, and you ask the adversary to produce this these P and Q. The probability that any adversary is able to do that is negligible. That's the factoring assumption, right? You know, this has been open for something like 300 years. People have tried to find efficient algorithms for factoring, but they have failed. A lot of very smart mathematicians have tried this. So our confidence in the factoring assumption is pretty high. So note that, of course, if you had unbounded time, I can just try every possible P and Q, but what we are looking for is we are looking for a probabilistic polynomial time algorithm, and our assumption is that it cannot exist. So now let me start with a very simple construction for one-way functions, but for a special domain, for a special input domain. So one-way functions for special input domain D. And let me try to define what D is. So sorry, there's a question. The probability doesn't depend on adversary's random coin. I assume you're talking about this definition. Yes, it does. So I should say probability is taken over X and random coins of the adversary as well. And here the probability is taken over the choice of P, the choice of Q, and the random coins of the adversary. A good point. So now if we are talking about one-way functions for a special input domain, the input is only supposed to come from this domain, and the guarantee that the function is one way only holds if the input comes from this input domain. If you choose some other type of input, inverting might be very easy. So what is this input domain? Well, this input domain just consists of sampling 2 primes. So D is defined as follows. In fact, it's probably easier to look at D as a distribution. So it just says sample P comma Q from P of n. And then you output X, which is P concatenation Q. Okay. So the input X is guaranteed to have 2 n-bit primes concatenated with each other. And now the function, one-way function f, is defined on this D, and it works as follows. So f of x works as follows. So step 1 is interpret the input x as P comma Q. So x is supposed to be 2 n bits. You first pass this input, you divide it into 2 numbers, n bits each. And then you output n equals P times Q. Okay, very simple. Now my claim is that given the output, it's actually difficult to compute the input. And as you can see, that almost directly seems to follow from the factoring assumption. Factoring assumption says that given n, you cannot compute P and Q. You can do it only with negligible probability. And we will do a formal proof of this. So this is great as an intuition, but as I mentioned in this class, if we want to try to prove things formally, and this will be essentially our first proof of security, and probably the simplest proof of security, because as you can see, this almost directly follows from the factoring assumption. But what I'm trying to convey here is really how to write a proof of security and what a proof of security means. So let me take some questions. For the factoring assumption, P and Q are output by the adversary. Why do they need to be random? I think they only need to belong to P of n. So it's very important that you choose the primes at random. For example, if you always choose fixed primes, then the adversary might already know those primes, right? So P and Q are not output by the adversary. P and Q are chosen first, and then you construct capital N out of these. And the factoring assumption only holds if you choose P and Q properly at random. Doesn't the factoring assumption assume that both P is not equal to NP and factoring isn't at P? So as written, factoring assumption doesn't assume that P is not equal to NP, although the fact that P is not equal to MP is implied by the factoring assumption. So this is a sufficient statement, and it also already implies that P is not equal to NP. Because if P is not equal to NP, then factoring just becomes easy. Factoring also assumes that the average case is hard, not that there exists a single PQ pair which is hard. Yeah, so the assumption, as I stated, it essentially assumes that average case factoring is hard. right? I'm just saying that you get P and Q at random. So I'm really talking about like an average prime here rather than a special prime. And the factoring should be hard for primes chosen like this. So D equals P concatenation Q, P is, yeah, exactly. So yeah, you wrote it more formally than I did. Good. Any other questions? Actually, let me erase the left side of the board and we will try to do the proof here. Okay, so we will try to prove that this construction is secure as per this definition. So now the theorem is that f is a one-way function with respect to this distribution or this domain D. Almost all the proofs in cryptography are done using contradiction. So assume that f is not a one-way function. Then what you want to do is you want to construct an algorithm A to break the factoring assumption. Okay, so assume not. So suppose you are given, so towards contradiction, you are given a PPT algorithm A which takes as input f of x and gives a preimage with noticeable probability. It's not with high. Okay. So what is the reverse of this definition? What would be the contradiction here? The contradiction here would be if there exists an algorithm A, which can give us the preimage, not with negligible probability, but with noticeable probability. And towards to complete the proof, we will construct another algorithm PPTB which takes as input capital N and gives the corresponding prime P and Q, hence violating the factoring assumption. And if we indeed believe in the factoring assumption, that means that there cannot exist such a B, and hence there cannot exist such a A. So B of N works as follows. So no prizes for guessing here. B of N invokes A on input N. Okay. Say A returns some X prime interpret X prime as, let's say, P prime concatenation Q prime. Check if N is indeed equal to P prime times Q prime. If so, output P prime comma Q prime. Else output fail. And my claim here is that if A succeeds, then B also succeeds. What does it say after preimage? With noticeable probability. With probability greater than or equal to noticeable of N. Why are we sampling both the primes independently in the definition? So suppose both primes are the same, then N equals P square, and taking square root is actually not that hard. So maybe there is some special distribution where P and Q are derived from each other and still factoring is hard, but the most natural definition is you start with independent P and Q. And now here's my claim. If F finds a preimage with noticeable probability, then, sorry, not F, A. Then P factors with noticeable probability as well. And here you can clearly see that the success probability of B and A are the same. So this is essentially the end of our proof. Any questions? All right, so our next goal would be to design one-way functions for a uniform input domain as opposed to this special input domain. And our very high level idea would be as follows. So our input would be uniform, but it would be large. And we will try to look for primes in the input. If we find 2 primes in the input, then we will multiply them and we will put them in the output. And in that case, we would be guaranteed that given the output, finding the entirety of the input would be hard. Unfortunately, if we don't find a couple of primes in the input, then this construction doesn't work. So we need 2 things. First, we need to understand what is the probability that a random number is prime. Second, we will want to start with a large enough input so that we can indeed find 2 primes in that with high probability. Okay, so we will rely on Chebyshev's theorem on density of primes. So Chebyshev's theorem essentially says that the probability that P is a prime such that P is chosen uniformly as an n-bit number, this is greater than or equal to 1 by 2n. So primes are not that rare. If you choose a random number, then there's some noticeable, reasonable chance that that number is prime. Okay, and we will not try to prove it. It's a fact from number theory. And now we will try to build one-way functions from this. One-way functions, one-way function f, and the input will be pretty long, n cube, and the output I think is 2 n bits. So this one-way function works as follows. 2 to the power n or 2, yeah, just 2n. So here is the description of f of x. Step 1, interpret x as a set S of n square numbers, each of n bits. Okay. So if x is n cubed, then you can write these down as n square numbers, each of n bits. The second step is run a deterministic primalty test. On these n square numbers. If we don't find a pair of primes, output fail. Okay. Otherwise, you output n equals pq, where p comma q are first 2 primes. Right. So by the way, this deterministic primality test is very important because as we mentioned before, the algorithm must really run in polynomial time. It cannot be a randomized algorithm. So testing if a number is prime or not, doing it in a deterministic way. This was an open problem for a while. And this was solved only in 2002. And since then, there have been some improvements which have been proposed. So thankfully, this simplifies the construction of one-way functions. So now observe that if the output is fail, the function is actually very easy to invert. Just pick n square numbers, none of them must be prime, and that's a valid preimage of fail, right? So we really don't want this output failed to occur too often. And this is where we will use Chebyshev's theorem. Okay. So overall, the theorem which we want to prove is f is a one-way function over uniform input domain. And before we get started with the proof, let me prove a very basic fact, and that will already sort of convince you that this is indeed a one-way function. So the fact is that probability of f of x outputting fail such that x was chosen uniformly from the required input domain is negligible. Okay. So what is the probability that f of x outputs fail? It's the same as the probability that you choose n square random numbers and we don't find two primes in there. Okay, so this probability of f of x giving you fail okay, this is the probability that very roughly that at most one number in this set S is prime, which is also equal to the probability that we have no prime plus we have exactly one prime. So these two statements are just the intuition, and now let me try to write more formally. So what is the probability that none of the numbers is prime? So this probability is at most the probability that one random number is prime, probability that one random number is not prime, it's 1 by 1 minus 1 by 2n and raised to the power n square. So what is the probability that exactly one prime? This means that the same thing, but you get it n square minus 1 times. And then the last or one of the numbers is by 2 to the power n into n square. And this comes from a union bound. Because we have n square numbers, this is the probability that the first one is prime, but none of the rest is, then you need to check the probability that the second one is prime and none of the rest is, and so on. So n square is just for the union. So this number as well as this number, they both are negligible. And I think the exact formula for this is less than, I think, 1 minus 1 by E or something like that. You can check the notes for the exact calculation here. But in general, the intuition is that whenever this is higher than this, significantly higher, you will end up with something negligible. So this is great. Now, at least intuitively, we have the following, that probability of the output being fail is negligible, right? So in that case, even if the adversary inverts the one-way function, we are fine. Doesn't happen too often. And now, rest of the time, there's a capital N in the output, and you need to factor that to compute the input. And the probability of adversary doing that successfully is also negligible. So now I need to describe.
So I have a small question.
Yeah.
So like even if like remember we did that example of f of x equal to 0, like even if we are outputting fail, isn't the probability of the adversary being able to reverse it very low still? Like we proved this is good, that like we will not fail most of the times, but like even if we were outputting fail, from going from fail to the input is like almost a random guess, right? Nobody can guess what was the input if you just give them fail.
So we are working with, let me show you the definition of one-way functions. So we are working with this definition. So adversary only needs to output some x prime, which is a valid preimage, such that f of x equals f of x prime.
Okay, you are saying so the adversary can output any of those which don't have a prime number in it. Okay.
Exactly. Yeah,
Okay.
adversary just needs to choose n square numbers such that none of them is prime, and then that will be a valid preimage. And that's
So
something.
it is not a one-to-one one-way function. That's why what I said is wrong, right?
Yeah, exactly. This is not a one-to-one one-way function. Yeah, otherwise you can just always output fail, and that's never going to help you.
Okay. Thank you.
So now let's try to arrive at a contradiction. Armed with this fact, we will try to construct B. So suppose this f is not a one-way function, okay? We will again build B to factor some given input n. And B of n will work as follows. As you can expect, B of n will invoke A of n, okay? See the preimage and look for 2 primes which lead to n. If such 2 primes are not found, output, let's say, abort. I don't want to use fail again. And now our goal is to consider the probability that A of n gives something with P and Q. So what is this probability? Okay. Ideally, I would like to say that this probability is equal to the success probability of is it equal to the inverting probability of A of f of x? Is that true? So here, unfortunately, this is not true. This is because of fail, right? Here, I'm never giving fail as input to A of n, but normally f of x sometimes would also have fail if f of x is computed correctly. So I cannot make a claim like this. And since I'm running out of time, let me just do a very high level proof sketch. You can see a formal proof in the notes. So this probability that it outputs P and Q such that P and Q are primes, and N is just PQ. So this is what I want, and this probability is equal to, and let me just call this to be success for A. This is equal to the probability that A is successful conditioned on f of x equals fail into, actually, I think let's get rid of this first equation. Probability that A is successful into probability that f of x equals fail. And by the way, here we will have the conditioning that x is generated at random. Thus probability that A is successful given f of x is not equal to fail into probability that f of x is not equal to fail. So this, as we have seen, this quantity is negligible. And this probability is at most 1, right? So this is just negligible of n plus we get this term. This is less than equal to plus probability that A is successful such that f of x is not equal to fail into probability that, and let me just substitute this probability by 1. Okay, and now we note that this is noticeable. So this means that the probability that A is successful given f of x is not equal to fail, this must also be noticeable. if f of x is not equal to fail, this means that f of x equals capital N, which is a product of two primes, which means that when A is given capital N, which is a product of two primes, A is successful with noticeable probability. And this essentially also implies that B is also successful with noticeable probability. So any questions? So at a very high level, our worry in this proof was only the following, that if we are given an adversary which expects the output of a one-way function, right? But the output of a one-way function might be capital N or it might be fail. If we prove that the output of a one-way function is fail with very small probability, that means that the adversary must invert at least some of the times, some noticeable fraction of the time, even when the adversary is given capital N. And if the adversary is doing that, that means the adversary is factoring numbers.